Who uses hydrocarbons in their business right now? Who doesn't is probably the better question, as he just said. I would start by saying that carbon capture is a way to keep using those energy sources while mitigating the emissions impacts on the back end. And so maybe that's not what we want to do forever, but instead of a rip and replace right now into new technologies, carbon capture can be a way to continue to use the infrastructure and the equipment that we have spent 125 years or more now at this point building out and continue to deliver value to society going forward. I want to start with just some terminology so that we're kind of on the same page on what carbon capture is and what different words mean. So there's a couple of different areas that people will talk about. They'll talk about carbon reduction versus carbon removal. And while those words might seem synonymous, it's very different implications based on what you're doing. And really they're talking about the application of the technology and the source of the carbon that is being processed. So carbon reduction means I have a point source emission of CO2, whether that's a power plant, an industrial facility, whatever it may be. I'm then going to apply a technology to that point source to mitigate that point source. That is carbon reduction. Carbon removal means by applying this technology, I am literally going to take CO2 that was in the atmosphere and I'm going to pull it out of the atmosphere and basically contain it in that way. So that would be things like direct air capture would be an example of carbon removal. The difference there is important because in the different voluntary markets and things like that, those are received differently in some cases. Most of what I'm going to talk about is really focused on carbon reduction, though. Once we're actually talking about technologies that can do that, there's really a few different ways we can get there as well. So one area would be pre-combustion carbon capture. This really just means I have this fuel. I'm going to modify the fuel to basically produce hydrogen before I actually do any combustion work at that point. So that would be like blue hydrogen. I take natural gas, I do steam methane reforming, I pull out the CO2, I have a pure hydrogen, then I can do something else with it at that point. Another option would be post-combustion CO2 capture. That means I take my fuel, I burn it, however it is that I'm doing that, and then I apply a technology to address the carbon emissions. This would be something that you could do at like a power plant, or it could be a retrofit even for any type of industrial facility. This is the largest area of carbon capture really at this point. And then it's not necessarily carbon capture, but another way to achieve carbon reduction through technology would be oxycombustion. And really what you're doing there is you're trading a separation technology on the back end for a separation technology on the front end. Instead of burning my fuel in air, I'm going to do air separation, produce pure oxygen, and burn my fuel in pure oxygen at that point. And then the outlet stream should be basically pure CO2 that is ready for transportation and sequestration or use at that point. So this is really a challenge of separation. That's all we're trying to accomplish, is to separate CO2 from everything else in the process stream. Because this is a challenge of separation, there's some different components to consider. One, if there's a lower concentration of CO2 in my stream, there's a higher normalized penalty for me to remove the CO2 from that stream. A really, really rudimentary example I would give is I put a bowl of marbles in front of you. And they're blue marbles and they're red marbles. If there are 50 red marbles in the bowl, when I tell you to find me 10 red marbles, that's going to be way easier than if I handed you that bowl and there were 10 or 12 red marbles in that 100, and I'm asking for the same thing from you. So every red marble will be easier to find if there's more of them to start with. If you have a higher concentration of CO2, it's easier to separate it from the rest of the stream. We also need to be able to maximize the efficiency of these processes to minimize the energy demand. Really, all of them are, I am putting in energy and I'm using equipment to do this separation. The less energy I can put in, the better. And then the smaller I can make my equipment, the more I can reduce my capital cost and the cheaper that process will be as well. There's different applications that may dictate different technologies that you use to make this separation happen. That could be based on the characteristics of the process that you want to mitigate. That could also be based on what am I going to do with the CO2 hereafter? What's the next application for it? Most current abatement applications are focused on post-combustion capture, and so that's really where we're going to focus today. That even applies to blue hydrogen. I know I gave that example as a little bit of a pre-combustion example before, but it may be that you really use a post-combustion application to create the blue hydrogen as well. So this is a pretty simple schematic of what a blue hydrogen facility could look like. You take methane, you're putting that into the steam methane reformer. You then have water gas shift on the back end of that, where you're converting that CO to CO2 and creating more hydrogen as well. There's a couple different places then that I could do carbon removal at that point. I could do it immediately on the outlet of the water gas shift reaction because I have CO2 at a higher concentration right there, and it's at pressure. And so a lot of people would say, hey, that's the easier place to do CO2 separation. But if I'm actually trying to drive toward the lowest carbon intensity hydrogen that I can, I actually want to take the off gas from the heater for the SMR and actually do my carbon separation there. Then I'm actually going to be getting all of the CO2 that is part of the process, not just CO2 on the outlet of the water gas shift. Typically, our water gas shift reactors are not resulting in zero CO on the back end of that. And so you have that recycle loop that you'd be missing if you did a pre-combustion capture versus a post-combustion capture. There are four major types of technologies that are being developed to do this separation. On the top left, you have absorption. That's using a liquid solvent to capture CO2. The typical arrangement would be that you have this absorber vessel where you have solvent entering the top of the vessel, the gas enters the bottom. As they cross in that vessel, CO2 goes from the gas phase into the liquid phase. At the bottom of that vessel, then, you collect that liquid and you send it to another vessel called a regenerator, where you apply heat to produce pure CO2 at that point. The benefits of systems like this are that very high capture rates are possible. This is typically a chemical reaction in most applications, and so CO2 is very, very well selected by the solvent. It's also a very pure CO2 product stream, and the component processes are really well understood. We use absorption, distillation, separations throughout refining and the chemicals industry, and we've done so for decades. We understand how these things work. The challenges, as Rick mentioned, why this isn't being done widely at this point, it's big equipment, and it's really high capital costs. It's expensive. It's a significant energy penalty, and it's typically a pretty high-grade heat is a component of that energy penalty. And we've got the potential, if we don't do this right, for creating new volatile non-CO2 emissions. So we don't want to trade a CO2 problem for some other emission problem as part of that. But a lot of the current work right now is trying to address, for instance, that emissions question, make sure that we have tight control and design of these systems so that we don't have unintended emissions. And then a lot of work is going on trying to drive down both the capital and the energy penalty and figure out how to better integrate these systems with technologies. But you can go get commercial guarantees today from a handful of different major vendors for solvent-based carbon capture systems. They are commercially available for those willing to pay at this point. The next most mature set of technologies would be adsorption. That's carbon capture by a solid. So this is going to be some type of material that, through a combination of its physical and chemical properties, will allow CO2 to bind with the surface of the solid material. So typically it's encased in some type of vessel. You flow the gas stream through that vessel. CO2 binds to the solid and everything else leaves. Eventually you take that vessel and you flip it from adsorption mode to regeneration mode, where you apply heat and or swing the pressure, and that allows the CO2 to be produced as a product at that point. The potential benefits there, eliminating water can decrease the energy penalty. It's still possible to get a very pure CO2 product stream. You have less potential for volatile emissions that you don't intend because it's a solid gas interaction. And the component processes are really well understood. We use sorbents for other things in other industries as well. The challenges, it's still big equipment and it's still high capital cost. But trading that liquid for that solid also means that material durability and reliability becomes even more important. if you have degradation of a liquid, you can bleed and feed and kind of make up the system. If you have a solid that degrades, you're going to have to actually stop and remove that material and replace it with a different material or a reconditioned material. It's a little bit more invasive at that point. And then it's really difficult to have a intensified process in some cases, because it's hard to get to the point where you have all of your material either catching or producing CO2 simultaneously, especially if you have process variation and things like that. But there are also folks that are out there pretty close to offering adsorption technologies on the market today. Both of those technologies are really economies of scale, the bigger the better, and they're thermal-based processes. The technologies on the right are kind of taking a different tack. These would be electrifications of carbon capture, and they're more modular in nature. The first would be membranes. This is separation across a barrier. So this is typically going to be some type of polymer or other material where CO2 would be allowed to pass through, but other things would be retained. Specifically, you're trying to be very selective of CO2 over nitrogen in most cases. You compress the gas stream and push it through a vessel containing the membrane. CO2 crosses that membrane and is then collected as product. Everything else is retained and then allowed to vent at that point. The benefits, this doesn't require heat input. So if you don't have excess heat or a heat source easily accessible within a process, you don't need one to use a membrane. It's typically smaller equipment with lower capital costs because they're compressing the gas stream and doing this at slightly elevated pressure. And you don't have a potential for new emissions. What's going into that vessel is coming out one of the two streams. It's not going to add anything to your process. The challenge is, again, this is a material that needs to be durable and reliable. If that membrane broke down, you would end up with impure CO2 that would not be suitable for whatever your disposition case was. If it plugged, you don't get the CO2 removal at that point. So you need it to be able to actually maintain its performance. It's difficult to achieve the same degree of CO2 purity or capture rate. That's basically because of the inherent properties of a membrane. It operates based on a differential in partial pressure or concentration. And so as you remove CO2 from the stream in question, you have less and less driving force to create that flux across that membrane. And so you end up needing more and more and more area for every amount of CO2 capture that you can do. It means it's very difficult to go to very low concentrations of CO2. And then your lower capital costs are going to be offset by higher O&M because compression is expensive. But it may make sense in certain industries. And then cryogenic would be the newest set of technologies on the block. This is separation by phase change. And I don't really mean cryogenic purification of CO2. That's been around for a long time for higher concentration streams, north of 50, 60% CO2, where you're just liquefying it and collecting it at that point. This is really targeting typical flue gas type emissions and using the fact that CO2 will change phase as the way to separate it. Specifically, you are cooling and compressing the gas stream to the point where you reach CO2's triple point, and typically then moving it from a gas straight to a solid, desublimating gaseous phase CO2 into dry ice, and then you're separating the solid from the gas at that point. Typically then it's melted into the liquid state and can then be either disposed of that way, shipped out by truck, train, whatever it may be, or you can then just use a pump instead of a compressor to put that CO2 into the supercritical dense phase for pipeline transportation. The benefits, this is again smaller equipment with lower capital cost. You've got the potential to co-capture other pollutants, so things like NOx, SOx, heavy metals, those typically will condense before you get to the conditions where CO2 will change phase. And so if you design your system correctly, you could collect those other pollutants as part of your CO2 capture process. You have also a very pure CO2 product in a liquid state. That opens up a lot of different potential use cases for that CO2. The challenges, this could be difficult to scale to really large flow rates. The reason for that, there's only so big you're going to build a compressor. There's only so big you're going to build a cold box. There's only so big you're going to build these heat exchangers. You hit a linear cost curve and kind of a modular pricing scheme more quickly than you would with other technologies. Your lower capital costs are also offset by higher O&M. You're still doing compression. We're also doing refrigeration in this scenario. And you have a lower technology readiness level. There's some analogs in, say, like the LNG space to the types of equipment that could be used for cryogenic separation, but this is not something that we have as much experience with as some of the other technologies. So just to recap, on the left, you've got economies of scale, thermal-based systems, chemical processes. On the right, modular electrifications of carbon capture. What's going to make the most sense in a given environment is going to be dependent on both the plant that you're trying to treat and the energy situation that you may have. If you're in an area where electric capacity is available, maybe that makes the ones on the right a little bit more palatable. If you're in a situation where you've got a bunch of excess heat, maybe you want to pick one of the thermal processes. None of them have an inherent advantage over the others. It really is going to be very situational on what you're trying to address. Just to summarize the current state, amine solvents are commercially available and are ready for deployment. You've got multiple major technology providers that can write commercial guarantees that you could actually count on, and the current development is really on trying to do process intensifications and understand integration better. The other technology types continue to develop, but may be more applicable for industrial sectors rather than power, where I come from. Sorbent systems, they must develop the system around the carbon capture material. Polymeric membranes are technically proven for higher concentration streams, but they probably aren't going to scale down to things like natural gas combined cycles, for instance. And then cryogenic separation remains at a pilot scale, but does hold some potential. I'll also say that direct air capture remains at least an order of magnitude more expensive than point source capture, and the thermodynamics just dictate that it's probably going to stay that way. So if anyone says, I don't want to look at point source capture, I just want to do direct air capture, you may want to rethink that and question whether that's going to be economical going forward. Just to give you an idea of some of what the deployments look like at this point, these are some major deployments in power. The Boundary Dam project in Canada was the first of these that came online. That's a 115 megawatt coal plant using the Shell CANSOLV technology. It's 700,000 to 800,000 tons a year of CO2. There's also Petronova in Texas. That is MHI's KMCDR technology. That was on about 240 megawatts worth of coal power and 1.4 million tons a year of CO2. And recently there was an announcement in the UK that the net zero Teesside power station would be moving forward into construction. That is going to use a GE natural gas combined cycle, a new build combined cycle with the Shell CANSOLV technology to capture 2 million tons a year from that combined cycle and then store it in the North Sea. So we've got examples on coal of this technology working well. We are going to then see developments on the natural gas combined cycle side. We also have, and I realize everything is up in the air these days, but the BIL demonstration projects out of the Office of Clean Energy Demonstrations. That included 2 combined cycle applications that Calpine is the owner of, looking at the Shell CANSOLV technology as well as the Ion Clean Energy technology, and then Project Tundra, which would apply the Mitsubishi technology to a lignite coal plant in North Dakota. So we do start to see some first movers on carbon capture and power, but we're also starting to see deployments in other industries as well. An early example of that would be the Great Plains Synfuels plant in North Dakota, which has been using physical solvents for coal gasification for that would be almost 4 decades now at this point. But we're seeing that move into other industries as well. In Norway, there's the Brevik cement plant project using the Aker carbon capture technology that has been deployed at 400,000 tons a year. And then here in the U.S., we're also seeing blue hydrogen applications for ammonia or hydrogen directly in the OCI plant in Texas using Lindy's technology, and then the Louisiana Clean Energy Complex by Air Products as well. And all of these are going to be many millions of tons a year of CO2 being captured and stored. The hydrogen hubs, there were also several of those that, again, are early stage and things are up in the air, but they were targeting blue hydrogen applications for at least a portion of their hydrogen production as well. I am from the National Carbon Capture Center, and I'll just close by kind of giving you a little bit of a rundown of that. This is a DOE-funded cooperative agreement where Southern Company provides infrastructure for technology developers to come in and test carbon capture technologies in a real-world environment. So at one of our power plants, we have built a test site. Everything is provided there for technology to come and actually do the carbon capture on either a coal plant flue gas or natural gas fired flue gas as well. So that means we have all the utilities prepared, we handle all the permitting and things like that, and technology developers really get to focus on driving their technologies forward. We also have a set of industrial co-sponsors that help provide some of the cost share and then also provide their perspective both to DOE and to the project or the technology developers that come in. And so the idea there is that we're having industry speak to the development of technology so that it's not growing up in kind of a vacuum and then having to adjust to industry later on. We keep a staff on hand whose whole job is not to run the power plant, but to support the testing. And the idea there is that we can actually help move technologies through the valley of death easier. I don't know if you're familiar with the valley of death, but the idea is there's a lot of funding sources and a lot of support for really early stage research, and then industry is really good at taking things over and actually deploying them once they're ready. That meaty middle, though, when you're starting to get into field pilots and then kind of small commercial demonstrations, that can be the most difficult time for a technology to find opportunity and support to succeed. We're trying to help things move out of the lab and through kind of the early stage field testing to where then it's ready for industry to take it over at that point. And that's really the focus of our project. We think that's been really successful. If you look at some of the deployments, I mentioned kind of some of the government-funded projects out there. These are kind of the large-scale developments on that. Includes both the demonstration program and then some large pilot and feed studies as well. Everything you see with a blue background, that is a technology that is part of its development has come through the National Carbon Capture Center, and we've been able to support. And we think that by coming and by getting that exposure to the correct type of environment, it has helped these technologies mature much more quickly than they would have independently. And that is the end, and I'll hand it off, I guess, now to Damien.